Hey, what's up, guys? This is Sean here. So today, let's take a look at this problem number 351, Android unlock patterns. Now, this one got a lot of downvotes because the description in this problem is not that clear enough. So I'm not going to vote this for now. So, I think most of you guys know if you guys have Android cell phone, there's like this kind of the keypad, right? Basically, you can create your own unlock patterns. Basically, you use your fingers to swipe on this keyboard on this keypad here. So, and for this problem, you're given like a 3 by 3 keyboard from 1 to 9, and then it also gives you two integers m and n. But this m and n is nothing else but the range of the number of the keys. Okay, so basically you have a range m and n, right? So m to n. So your unlock patterns has to be within this range here. It's just that. Okay, so this range is of course is from 1 to 9, right? And then here's the more important part. Basically, the rules of a valid pattern, right? So each pattern must connect at least m keys and at most n keys. So this is the basically telling you the range of your key patterns. And the second one is that all the keys must be distinct. This is also kind of easy to understand, right? So you cannot type one key uh, more than one times. And the third one is the most important. Okay, so if the line connecting two consecutive keys in the pattern passes through any other keys, the other keys must have previously selected in the pattern. No jumps through non-selected keys is allowed. Okay, so I think I can just use this example here. So basically, okay, here. So we have 1, 2, 3, 4, 5, 6, 7, 8, and 9, right? So the third rule is like this. Basically, you can only move first. You can move to any adjacent node here, key number here from 1 to 2. This is allowed. Okay, but from 1 to 7, from 1 to 7, this is not allowed because the 4 is not selected, didn't get selected before. So if you want to move to 4 here, you have to 1 to 7. So the 4 must have been previously selected before. That's the second case. And the third case is the diagonal is also allowed. Basically, from 1 to 5, this is also allowed because from 1 to 5, from 1 to 5 here, right? From 1 to 5, you're not touching the 2 or 4 here. You're only touching 1 and 5. So this 1 to 5 diagonal ones is also considered as a adjacent number, right? But from 1 to 9 it's not allowed because basically from 1 to 9 you're passing 5 here, right? So which means you need to have the 5 previously visited before, and then you can do 1 to 9. Okay, so I think what confused most of the people is like this night move. For example, from 2 to 9, from 2 to 9, or from 4 to 9, or from 8 to 3. This is called a night move. So the night move for this problem, it's basically it didn't considered as touching either 5 or 6 or 8. The reason being is that, I think this problem, it didn't tell us very clearly, you know, only the center point, for example, if the for each of the keypad here, right? So only the center point, only when you pass through the center point of this square, then it counted touching as pressing this button. For example, if you move from like this 9 to 2 here, right? So this is 2, this is 9 here. See, even though you're passing 6 and 5, but you're not passing the center point of the 6 or the 5. That's why the knight move basically is basically a free move. You're free to move. You're free to make any knight move because for any knight move, you're not passing any of the center of the other numbers, the other boxes, right? So that you can just consider this knight move as like a pass, like moving between two adjacent numbers, right? So I mean, this is a really confusing part. I think that's why a lot of people downvote this problem because it didn't tell us very clearly you are free to do any knight move, and it didn't tell us that only passing the center point of any button considered as pressing this button. Yeah, so I think that's the clarification for this problem. And as long as we can figure out this kind of knight movement and also kind of the the cases that we need to validate the moves here, now the problem will basically becomes like a DFS, or we call it a backtracking, right? Basically, we just try to start at all the at each of the numbers here, and then from there we just we have this like kind of remaining numbers we need, right? So let's say for example from 1 here, and if we want to have like a 2 movement, right? The movement is 2 here, and so from 1 we just need to try all the possible numbers, right, at each of the movements, and we'll find the valid movement, and then we just keep going until the remaining number is 0, and then we know, okay, we find a valid unlock pattern. Okay, so and to be able to find the valid movements, for example, from 1 here, uh, we can only move to what? To 2, 4, and 5, right? Sorry, yeah, sorry, 2, 5, 4, and sorry, plus all the knight movements. Basically, from 1 to 6 and from 1 to 8. Basically, from 1 we have a 1, 2, 3, 4, 5. We have 5 valid movements from 1, right? So that's the yeah, and then we just keep going until we have consume all the remaining numbers. Okay, so to validate the valid move for the next valid movement, we have, of course, we need to maintain like a visited or seen set, right? For the numbers we have seen so far, because we cannot press one button twice. And the second one is that how can we know the for example, if from 1 to 3, right? So from 1 to 3, if 2 is not visited, then we know, okay, 1 to 3 is not a valid movement. Okay, so to do that, I mean, you can either use a math, right, to calculate to use the rows and the columns of the integers to do some like a divided, or to do a mod of that. I think you can do that. And I also seen people doing that. But a more or like a easier way is that we just list all the cases, right? We just list all the cases that we need to skip the middle one. So how many cases we have here? We have 1, 2, 3, 4, 5, 6, 7, 8, and 9, right? So how many cases we need to consider the 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 middle number, right? So from 1 to 3, 1 to 3, and 3 to 1. So in this case, if it's 1, 3, or 3, 1, we need to check if 2 has been seen before. Same thing for 1, 7, and 7, 1. So for this, we have to check 4, and this we need to check 8, and here we need to check 6. So that's the 8 cases, and also the ones in the middle, right? Basically from 1 to 9, we need to check 5. 7 to 3, we need to check 5, 2, 8, and 4, 6. So for those cases, they're all sharing. We all need to check if 5 has been visited or not. Okay. So for this one, we can just simply maintain like a dictionary to maintain the if we have seen 1 and 3, and then what will be the numbers we need to check. Okay. So that's that. And yeah, so since we need to check the current number and the previous number, so in our backtracking method, we also will also be maintaining like either a previously visited number. Yeah, I think we will be maintaining a previously visited numbers, and then we use that to make a pair so that we can check if there's any numbers we need to in the middle we need to check. Cool. So I think that's that, and we can start the coding here. And let me see what should I do here. So first, we need a backtracking method here, right? So the backtracking, uh, we need to have a card number, right? So and then we have a remaining like the remaining numbers we need to make our current unlock pattern, right? So that's our backtracking method. And then we have I'm going to create a skip uh, dictionary here. So basically, like I said, we have 1, 3. So for 1, 3, we need to skip 2. Okay. And then for 3, 1, we also need to skip 2. Okay. And 1, 7, 1, 7, 4. Okay, I actually know what I'm gonna copy these things here. 4 and 7, 1, 4. Okay, actually, I've already write it down somewhere here. So that's the basically that's the skip dictionary here. As you guys can see, we have from 1, 3, we need to skip. We need 2 is skipped, and 7, 1, 7, 7, 1 is 4, the 6, 8, and this is our other cases for to skip 5, right, in the middle. So now we have that, and we can write our main loop here, right? So we have an answer here. Answer is equal to starting from zeros, and then we need to loop through the basically the m to n plus 1, because so basically we're trying all the possible numbers of the length of the patterns, right? And then for each of the length we try all the numbers, because we start in range of the 1 to 10. Okay, so that's our starting point. And then for each of this starting point, I'm going to maintain like a scene set. Okay, so for each of the loop here, so we have already seen this start point, and then result plus backtrack, right? Plus backtrack, we have a start point, and then we have a I minus 1. Okay, because we have seen this one, so the remaining one is I minus 1. Okay, so the reason, like I said, so we're maintaining the previously visited numbers here, so we can so later on we can use the previous one plus the next one to check if there's any skip numbers we need to verify. Okay, so and in our backtracking method, and let's write the base case. So I think the base case is pretty straightforward, right? So if the remaining is 0, and then we know, okay, we have find a valid unlock pattern, so we can simply return 1 here. Okay. Otherwise, we have answer equals to 0. Okay. Otherwise, right, we just try we just loop through all the numbers here. So I'm going to call it next number. Okay, in range 1 to 10. Okay. Basically, I'm just try all the numbers from 1 to 9, and we try each of them to see if that number is a valid next number. Okay, so how do we check that? So first thing first, right? If the next number has not been seen before, that's the first one, right? So the number has not been seen before, and what? Now it's time for us to check uh, if this number, if the next number and the current number uh, is part of the skip here. Okay, if it's part of the skip dictionary here, and then we need to check if this the numbers in the middle has been visited or not. If not, then it's not a valid. Okay, so basically here we're gonna write two conditions here. So first condition is that if the current number and if this pair, the current number and the next number, it's not in skip. Okay, if it's not in the skip, and then we know, okay, cool. So this one is definitely a valid next number. Okay, or since this is an or here, right? So when we add or here, we know, okay, so this one is in the skip. So now we need to check if this skip dot current number, if this pair, okay, so if this pair is in the scene, right? So basically, now we know, okay, so this pair is in the skip dictionary, and then we just need to check if the skip number has been seen before. Okay, then we know, okay, so this is also like a valid pass, right? So then we can simply do a scene dot add, right? We add this one, the next number to the scene set. That's why we call this backtracking, right? And then the answer will be the backtracking. We accumulate this valid path, right? To the current answer. So the backtracking, now we have a starting point. Now the next number, right, will become the starting number for the next backtracking method, right? And the remaining numbers, we just do a remaining -1. Okay. And here, don't forget to remove these numbers to complete our backtracking logic. Okay. And in the end, we simply return the answer. Cool. And of course, so here we have an answer, and I'm going to return the answer in the end here. Yeah, I think that's it. This should work. Let me try to run the code here. So the one case works. Submit. Cool. So yeah, I think it works. And I think there is like a little bit improvement we can make here. Instead of here's the improvement here. If you watch this like pattern closely, there's some symmetric observations here. So what does it mean? It means that we have 1, 2, 3, 4, 5, 6, 7, 8, and 9. So here, as you guys can see, we're looping through all the numbers, all 9 numbers here, from 1, 2, 3, 5, 4, 5, 6, and 7, 8, 9, right? But if you watch it closely, there's a pattern, right? How many patterns do we have here? We only have 3 patterns. So the first one is the numbers on the corners. So which means we have 1, 3, 7, and 9, right? Since this board, this like pad is like symmetric, right? So starting from 1, 3, 7, 9 will give us the same result, okay? Because they're all on the corner, right? So uh, that's the first pattern. The second pattern, of course, is the numbers on the on the in the middle here. So 2, 4, 6, and 8. So anything starting from 2, 4, 6, 8 will yield the same result. Sorry. And the last one, of course, is 5. Cool. So what does this mean? It means that here we don't have to call this backtracking method 9 times. Instead, we can only call it 3 times to handle these 3 patterns. Okay. And cool. So um, here, let me see here. Mm. So we don't need this like this for loop here, but we still need this scene set here. So basically the first pattern is one here, right? So that's the first one. And oh, actually here I'm gonna yeah I'll just use this. I'll just I'll just use one to represent the case the pattern the case on the corner. So basically we have four corners. We can simply do a times four here, right? And the second case is the one on the two, basically 2, 4, 6, 9, right? As 2, 4, 6, 8. So I'm gonna use 2 to represent that one, and then we do a times 4 here. And the last one is what? The last one is 5, right? So the one in the middle. But here there's only one case for that. Cool. So yeah, so that's that. I think this should just work. Oops, sorry. Hmm. It's unbelievable. I think I made a mistake here. It should be 5, but it's still passed. Okay, so which is not correct, I think. Okay, cool. I don't know. I don't know something wrong. I think something wrong with the test case, but yeah, cool. And so let's see what's next. Yeah, of course, the time complexity, right? So the time complexity, so we have a m to n here, right? So we have there's a range here, so that's the second one. The second one is the let's call this one mm, I don't know, maybe a k here. So that's our first loop here, right? So the k times what? Times the backtracking. So what's the how many possibilities we have here? Let's assume we have 10 numbers here. Let's say the number is n here. Okay. I know 9 is like a fixed number, but let's just use 9 to represent total numbers on the pad here. So we have a so the first one we have a 9, we have a n possibilities, right? And then the second one is like what? It's n minus 1, right? Because we have already seen those numbers. And then the next one is n minus 2 because we have because each time we have seen that number, so where there are like n minus 1 numbers left, and the third one is n minus 2. Let's forget about those the skip cases for now. Okay, only considering about looking at the main logic. So what do we have here? It's basically it's a n of the factorial, right? And yeah, this is the time complexity. Yeah, and space complexity. Yeah, space complexity. So this is just this scene like set here, right? So it's O of n, right? So this is the time, this is the space. Cool. So I mean, yeah, I think that's pretty much it is for this problem. I think it's a cool problem. It's only the only thing is that it didn't tell us very clearly about this night move. I mean, if it lists out that night move is like considered like a free move, and then this problem is definitely a cool problem. Okay, so basically, uh, the main logic for this problem is just a regular like backtracking method, with this current number and the remaining patterns numbers, right? So that after that we just need to find all the cases, right? We need to consider for us to make the next valid move. Okay, in our case, the next valid move is first the next number should not be seen before, and if the next move and the current move has a number in the middle, right? So and then we need to check if that number has been seen before or visited before. If that's the case, then the rest is just a regular backtracking template, right? And then in the end, then here it's just like a little bit uh, performance improvements. Basically, we're cutting down the backtracking call by 2/3, right? From 9 times to 3 times. Yeah, but the time complexity still holds the same. It's just like a bit of improvements here. Okay, cool guys. I think that's everything I want to talk about for this problem. Yeah, I hope you guys like this video. Thank you so much for watching this video, guys. Stay tuned. See you guys soon. Bye bye.